Second piece, reconstructing our PDF. Oversimplifying, but it only consists of 3 steps: splitting file into pages, splitting pages into sentences, and group or split sentences together forming chunk of sentences. SpaCy and all MPNet-based v2 will help us getting it done. We'll store the result in a variable. This piece at the end is going to use the variable created here. Let's run the first one. It is pretty fast. Let's view some sample data we get. For example, page 10 consists of these texts, page 12 these texts, and so on. This is a few lines for sample. We have our text and page number they belong to. This is a little summary. Let's run the second one. We'll test with simple sentence. It seems alright. Let's run the real thing, loop through our variable. And it's done, very fast. Let's view some samples. We can see, for example, that on this page we have this full text, and the texts are split into sentences. Let's run the third one, last. We define split size to turn group of sentences into chunks. For our case, it is not going to be much different because we have short sentences. It could be useful for a document type such as essay, journals, or those with longer sentences and more text than graphics or tables. Let's see, we have the same page. And, as expected, these are our chunks of sentences. Nothing really significantly differ from our previous step. Lastly, let's group them into sentence chunk. Think of it like a paragraph that consists of sentences. This is an example of it. And this is a little statistics. We have 46 chunks now. Should there be any chunk that is too short, we can remove that. For example, remove those with less than 25 tokens in length. Nice, we have reconstructed our PDF to pages and chunks. Moving on to the third, embedding. Given these 3 sample sentences, let's encode them, aka embed them, using all MPNet-based v2. And we'll print the sentence and its embedding result. Let's see. This is the sentence, and this is the factor representation. This is the second sentence, and its embedding result. And this is the last sentence. To simplify, this is the factor and size of a sentence. For testing, let's try to do embedding using CPU and GPU. Let's run using CPU. It takes quite a while. Now using GPU. And boy, it was fast, more than 10 times faster. Time to prepare the real text chunk. We make it a single list here and embed it using batch here. And our text chunk embedding is ready. The next piece consists of 2 parts. Save the text chunk embedding into CSV and also load it into torch.tensor. As mentioned, when we are dealing with larger dataset, please consider to use VectorDB. First, save it to CSV and preview it. These are the sentence chunks. Each one has its corresponding embedding value. Second, load it to torch.tensor and preview it. Now we have all we need. Let's see the next piece, embedding model. We have actually used this when we are comparing CPU and GPU performance for our sentence chunk. Just want to highlight its use because embedding model has limitation. In our case, the limit of 384 tokens is more than enough. Next piece, similarity score. Say we have a query or a question, we'll embed it using our model, get similarity score, and print other factor value closest to it. This is the top 5 closest value. What if we have thousands of embeddings? Let's test. Multiply this by 100 and run. It is still blazing fast. Now let's see the text represented by the closest factor values. This function is handy. And let's run this. We can see our query here and the result below. This is the first score with the text. Below that is the second score with the text. And so on. The score is getting smaller, which means the most similar one is on top. For fun, let's print the page that returns most similar answer. When I put the same page number as top value here, it returns the page most similar to our query. Moving on, I'm just creating functions here. These functions contain the same logic we know. And I'm calling the function here. Let's run. And it returns score and indices. Run this one. And it returns score and text. Again, most relevant result is the first one with the highest score. Jump over to LLM, our next piece. LLM consumes GPU. Let's check ours. This is our GPU capacity now. We can confirm it here. Let's run this code. It creates quantization config using bits and bytes. Then it downloads an LLM model or an LLM I've previously uploaded. We are using Gemma2BIT. Instantiate tokenizer, instantiate LLM. Take a while for a 5G model. Let's fast forward a bit. And our Gemma LLM is ready. No harm rechecking and we have enough resources. We apply chat template, tokenize our text, and spit its generate output. Nice, and let's do our magic, decode it. There we have text reply. Clean it up a little bit. This is our query, and this is the text reply. If we have several queries, we can make an array of query lists like this. Last piece, augmentation. We're not interested in general reply, although it was really cool, but we want to see reply within context of our PDF. And we already have pages and chunks. We'll use it now. Quickly run base prompt. This is nowhere near perfect prompt engineering, but should be sufficient for our simple case. And apply chat template. Now, the most important piece, our rect function ask. Basically, it uses pages and chunks for context items. Using LLM model, we'll generate output. Let's run it. A function is created. Let's take a query from our query list, and we'll definitely print its reply. This is our query, and this is the answer. Remove any excess coffee from the rim of the filter holder and attach it to the appliance. Press and hold the coffee button, yada yada yada. If we compare it, first prepare the ground coffee by placing it in the filter holder, then press the coffee button to initiate the brewing process. They are different, but they are essentially the same. They are similar. We are using Gemma 2 here, so different large language model from our notebook that is using Gemma. We have successfully augmented our query result. Let's now compare non-augmented output. In our notebook, we have this. And in Open WebUI, we have this. I should think they are similar, but that's not matter. What matter is that with the same query, how to make coffee, we can give context and augment the result. How cool is that? Future work. There are a lot of ways, techniques, or even tools that we can apply, or we can adjust when facing different environment, requirement, or size of dataset. I've listed some here. We always improve our way of working, so is this non-exhaustive list. At least we have seen RAG in action and how it works behind the scene. That's all for today. Bye.